right, well, I want to welcome everybody to our Friday Integrating Bioinformatics Education Series. My name is Dr. Liz Pierce, and I'm the moderator for the series. And today we are fortunate. We have Mr. Jeff Pummel, who's the co-director of the Arkansas High Performance Computing Center at the U of A Fayetteville. He also holds an adjunct position in the Department of Biological Sciences. And today he is going to be talking to us about the services and what faculty and students can take advantage of through the Arkansas High Performance Computing Center. So with that, I will turn it over to Jeff, and thank you very much for being with us today.
Thank you for that introduction, Liz. I'm glad to be here with everybody. We used to do these more often as far as intercampus between Arkansas institutions, and it just kind of during the transition of different management, certainly at Fayetteville, you know, we've just kind of gotten out of the habit, and I'm glad to get back to doing this again. Can everybody see the screen okay, the presentation?
Looks good.
Okay, great. So basically, we're the Arkansas High Performance Computing Center. It's a core research facility under the Vice Chancellor for Research and Innovations Office. I do have a couple of obligatory slides, you know, that the university likes me to run through really quick. So we'll pop through those, and then we'll get to the facts of the matter. Basic introduction. I was hired in, well, I guess first thing that happened was a computer science professor, Amy Apon, was rewarded with a NSF award number 421-1099 back in 2004 that allowed her to purchase a large-scale HPC system. In fact, it made the international top 500 list as one of the fastest 500 systems in the world at the time. What they found out with a resource of that size and complexity is you couldn't have a part-time grad student manage the thing. So I made a transition from elsewhere into the senior administrator position at that time. So I became I guess employee number one for AHPCC, and I started in October of 2005. So I've been with them. I'm coming up on 15 years, and as things grew, we didn't have a large base of users when we started. You know, 8 to 10 people, and you know, probably 2 or 3 disciplines. That quickly changed as things kind of ramped up. We were in kind of the golden age of large-scale computing on general academic research campuses. So we had a second NSF award and another top 500 system in 2008. Subsequent awards in 2010. We also, the need on the Fayetteville campus was so great that we actually acquired a very large system from San Diego Supercomputer Center in 2015. The large NSF centers typically run a system 3 years, and they basically surplus it. But I had the deputy director at San Diego was a friend of mine, and we arranged to bring that system to Fayetteville. So and it's still running. You can still use trestles. As of late, we had some funding from different sources, some of it from faculty, and we deployed the Pinnacle system last fall. It was kind of officially when it was stated. It really got running and people on it this spring, but it's kind of a new thing. It's got a lot of NVIDIA GPUs for GPU computation. A lot of the data science people like the GPUs, but we're seeing some GPU use in bioinformatics now. There are some applications that can utilize those resources. AHPCC core research facility at the U of A. It's under the Vice Chancellor for Research and Innovation. We do have affiliations with the National Science Foundation's EXCEED program, which is the National Supercomputing Centers. There's a short list of our grants. I hope I got them all. Those get increasingly hard to keep track of. The mission and vision, you know, is basically to support our researchers and our fellow campuses around the state of Arkansas, and the affiliates and collaborators of the faculty on these campuses. If you're a researcher at UAMS and you have a colleague at you know, a national or international campus, we are able to add those people for research as well. So if you have a sponsor within the state of Arkansas, you too, as an international or somebody outside of the state, can use our resources. So again, the little quick blurb about the systems. I mentioned a lot of systems on that first slide. Of course, most of those have gone to the boneyard. Basically, they're not a lot different than a server or even a desktop computer. They're composed of a lot of the same parts. And after 3 to 5 years, the power that's required to run them compared to the computing cycles that you get kind of ends up being a bit of a loss. There's maintenance issues and things. So typically, the life of a supercomputer is 3 to 5 years. Trestles has certainly been running a lot longer than that, but it was so large that we could kind of scavenge from one system to another to keep a lot of it alive. So that's why we still have it. But yeah, Pinnacle and Trestles would be the two systems that are available right now for use, both for UAF and any other campus in the state. Quick overview. So up in the corner is Dr. Jackson Cothran. Dr. Cothran is kind of the administrative executive director of both AHPC, the Center for Advanced Spatial Technologies. He's got a lot of irons in the fire, but he's kind of our administrative executive over things. On the main screen from left to right, standing in front of the trestle systems, Dr. David Chaffin. David's got about 35 years of experience in high performance research computing. He right out of school, he spent some time at Los Alamos on the very large DOE system. So as far as Fortran and the intrinsics of an HPC system, he's got more experience than all of us. I'm here in the center. I'm here basically for the science. I love the natural sciences, physics, chemistry, biology. That's always been my fascination since a kid. And that's why I do the high performance computing, is to enable those areas. That's again, I was the senior administrator and worked on the hardware for the first 5 years I was around, but it was all based on love of science and advancing the mission. On the right's Dr. Walensky. Pavel was a PhD student in computer science under the original director of the center, Amy Apon. He also worked for a time for a computational chemistry software code that was developed at UAF. So he's got a lot of background in the computational chemistry area too. So between the three of us, we keep the wheels moving, and we're pretty much distributed enough where one of us has some depth in whatever we're trying to resolve and make function. So HPC is the supporting entity for computational science. And I want to make a quick distinction here. We have a lot of trouble, like with news writers and things, confusing computational science for computer science or computer engineering. They're very different things. Computational science is the support of all science and engineering through use of high-end computation. It really doesn't have anything to do with programming languages or designing new circuit boards or anything like that. It's the use of large-scale computing equipment and software to enable research and exploration. So that's, you'll hear in the HPC ranks, you'll hear computational science used a lot. And that's what we mean by that. That's the hardware, software, the support staff, and the user community. That it's all makes up the environment. So when we get down to AHPCC use, and these charts pretty much show Fayetteville use. We're revising our methods of pulling up metrics to include people from other campuses, but that's kind of a slog. We're not quite there yet. But for Fayetteville use, this is kind of a breakdown of who uses the HPC systems. And while we have more people with accounts on the system, 707 are the users that in the last year have done something relative to research as far as using the computer. It wasn't just a log on and a log off or something, just getting an account. These are actual live users that have done computational use in the past 12 months. So obviously you've got chemical engineering, mechanical engineering, industrial, physics, chemistry, bioinformatics as a whole, and I'll break that down in the next slide, but bioinformatics takes up about 20% of our use. And other, and this will be, other is a large chunk, but what is in the other slot? Of course, there are people like finance, people like political science, that are doing unique things. But a lot of this other over here includes computer science courses. They're either undergrads or grads that have allocations. And since those aren't research, we don't break those down. I don't want to show a cross section of a pie chart that's 40% of our users, because it's not research affiliated, which is really kind of what the systems were grant funded to do, is research. So we have resources that we can get around that, that we can use for research and things, and there are parameters that we can do it. But I try to keep my graphs and my usage charts based on research, because NSF asks on occasion and they want to know what these systems are doing. If you take that 20%, you can break it down to the various bioinformatics users on campus. Of course, the Department of Biological Sciences, which I'm also a part of, is the largest part of the pie. Cell and molecular biology program kind of encompasses all of this. Dr. Rhodes and I are trying to figure out whether we should incorporate that or break those people in that program down into their respective programs. But between biology and agriculture, so crop sciences, entomology, food sciences, animal sciences, etc., that's where our distribution is for bioinformatics on campus. So why is bioinformatics and life science so much different than what HPC has done historically? And by historically, I mean scientific computing or supercomputing dates back pretty much in physics and chemistry, back to the early 50s when the big computers were coming out. It was all an offshoot of the Manhattan Project and people needing to do hydrodynamics calculations and thermochemistry and things of that nature. But it's maintained its pace in those areas. Chemistry and physics is probably still the largest consumer of compute cycles on most campuses. But bio was new because for a long time, the things that you wanted to do, T-stats or small sequencing runs off a 454 instrument or something, you could do that on a desktop. You didn't need these large cycles because of the way it was being done. When sequencing technology became so cheap and so available, then we had we were inundated with all these volumes of sequencer data, and the architecture of the supercomputers wasn't ideal for doing that. Supercomputers historically have a whole lot of individual computers tied together with a fancy network to run things across all of the computers. And biology software is not that way. Plus, biology software needs large chunks of memory and very long run times sometimes to do the tasks at hand. So we've spent a lot of time retooling and working towards that goal because we have so many biologists that we need to support. And this is just kind of an overview of that. They've historically spent less time on large computing systems with respect to the history of scientific computing, that is. Really large data sets. It doesn't take a lot of sequencing to end up with gigabyte files, so that's something you have to contend with, both in computing and movement, from desktop to supercomputer or between computers. You need large memory and disk space. And again, they don't run across multiple computers like physics and chemistry code does, so that's another limitation that you have to compensate for. Physics and chemistry, you'll have a user in chemistry that will use one or two applications through their whole career. Biology, as I'll show you in a minute, is there are just a plethora of software packages that are required for any given task. You do one task and then you move to another type of or a software with another purpose to further the research, and it's very software intensive. That's really kind of the biggest challenge with biology, is maintaining the software stacks and making sure that they function and that there are examples to learn with and things like that. Languages, Perl, Python, R, shell scripts, some of them are compiled. Something else we find in biology is the binaries that are available are typically, for the most part, they're Linux or Mac. If they're non-Perl or non-Python scripts, if they're actual built compiled applications, then they're not really available on Windows, and that's a hurdle we typically have to deal with. Delivery methods. That's pretty much kind of a general assessment of bioinformatics in the academia and research. So bouncing over to some of our resources, we have, in order to make things a little more straightforward rather than the old cryptic secure shell terminals and things like that, we adopted this OnDemand Portal from Ohio Supercomputer Center. They were funded by the NSF to build a more or less a web portal or a web front that you can install on a supercomputer and access the tools that you need to do your job. There's still a lot of intricacies behind the facade, but at least it's one step less. It's much easier to just click a web address, and at least you're logged into the supercomputer and able to do something. And with that, they've added a few interesting features that also lower the friction or the time to success for using these large-scale resources. One thing they've got, I guess we could go back one, I think this is under Files. When you log in, you can click and go to a web browser, and this looks very familiar to Windows and Mac users. It's just something that you can highlight a file and then tell it to, if it's on the supercomputer, you can tell it to download it. If you want to upload something from your desktop or your laptop, you'd highlight it, or I think you actually hit upload, and then you pick the file from your local resource and just click it, and it moves it up to the supercomputer. So that's one method of kind of streamlining things. The old supercomputer users from days gone by are used to using just a text terminal, and configuring things like secure copy and FTP and typing it all in, that's what I'm used to doing. So I'm a little awkward with some of these new GUI tools just because I've spent so long doing it the other way. But we found that these resources and these enhancements really speed up people's time to success when we're bringing them online to the resources. So another one you'll probably be seeing on at least at UAMS and probably UALR, and you can actually install this free anywhere, but we're trying to make these endpoints to some of the institutions available on 10 gig links. This is another NSF project called Globus, and the tool is called Globus Connect. This allows you to move large files, and if you'll look to the left here, these 4 files that I moved from our system, Pinnacle at UA Fayetteville, to a system at Pittsburgh, a large NSF supercomputer, where these 4 files, they're paired in sequencer files. They were 50 gigs combined, so it's not one of my bigger transfers, but 50 gigs is still something to kind of slow down progress. That we were able to transfer those at about 2.5 gigabytes a second, and that didn't take. I wish I had the spec. It was like 4 minutes or something like that to transfer and validate the files. So this makes things a lot easier when you're moving things around. What you'll find is that maybe you want to do some things on a resource at UALR. You've got a system or a resource you're used to using, and you break a bunch of files, and then you say, well, I need to move a certain number of these files to Fayetteville to the big computer to do one application. They've got it installed there, or it's a commercial code that we don't have, or whatever the case is. You don't want to spend all day trying to use a secure copy to move files to and from. So this is a tool that allows you to spin up multiple network pipelines to move big data really fast. And this is something that's pretty common among all of the big NSF centers, and most of the campuses are beginning to adopt it as well. Some of the other things on the portal, we call it Pinnacle Portal, but the tool is actually called OnDemand, and it's free for use to any research or HPC center, that's wants to adopt it. There's some configuration involved. Anyway, one of the things the system administrators have set up is shell access to the system. So Grace is at UAMS. They've worked it out somehow where we can pull up a secure shell on Grace at UAMS from Fayetteville, or a UAMS person using our systems can go ahead and pull a shell up to their HPC system at home. Karpinski's a computer science project. Pinnacle, we mentioned. Razor will be going away. It's an old cluster that's past its time, so we're going to mothball it. And then Trestles is the big system from San Diego. Something else we were able to do that's always been a problem with HPC systems kind of until now, you can do interactive applications. So something you typically didn't do on an HPC system or supercomputer was any type of graphical interface. You don't pull things up and have buttons and slide bars and things like that. They're just, the graphics is not on the front end one of the things that HPC supports. It's raw computational power to solve matrices or sort large bits of data. That's become, with big data, actually, that's become a situation that's changing. So what this allows you to do is to pull up one of these GUI-based programs on the supercomputer. It runs on a server over on the supercomputer, but it exports it. It's just a VNC session, basically. So it's running on the supercomputer. It has access to this big 50 gig chunk of data you're working on, but you can pull up a session on your desktop and run a something like integrated genome viewer here that keeps you from having to pull all that data back to your desktop if you don't need to. You can run your simulation, pull up the visual viewer, and do your assessment of your computational run right there on the supercomputer without having to move all the data around again if you choose not to. Something like this, for example, that's an IGV view of somebody's doing some stack ups of some BAM files from a genome analysis, probably looking at SNP variations or something like that. So that could actually run on the supercomputer and have to pull it over to your laptop or your desktop to do so, and if you choose to not. So there's the current data set I'm working with right now. This is a project Dr. Rhodes and I are working on. Actually, it's kind of we've spun it up again. We did some of this about 7 or 8 years ago with just Illumina data. And now with long read technology being all the rage, we've got this new file, this 115 gigs of long read technology from a Prometheon nanopore sequencer. So that's if you're doing material, if it's a eukaryote, it's very likely going to be, you always target about 100x coverage from whatever your genome size is. So, pushing 100, 200, 300, 500 gigs of data around is really pretty common these days. And that's just an example of the data sizes. 5 years ago, we started on the big craze, and people had a hard time defining what big data was. And being already involved in genomics, I thought, well, I got a pretty good idea what big data is. So with these large data sets, something that's been dragging behind a little bit is the ability to minimize the memory use or the resource use and speed up the simulations. I've got some applications that are running right now on that are taking 4 to 5 days improving data before it's assembled. So that's really kind of a slowdown in the workflow when they do that. So people have been working a bit on some of these existing code bases. BWA is a sequence aligner, and it's been around for a long time. He finally took the initiative to bring about the next generation of BWA. So they've worked over the code base once and are further refining it, but it's 1.3 to 3.1 times faster than the original BWA, and it's an indexing for memory is down from 42 gigs of memory down to 16, and they think they can get it down to about 10. So we're using a quarter of the memory, and it's 2.5 to 3 times as fast. And that's something that people are starting to look at, in addition to using novel architectures like GPUs to process data where it makes sense. GPUs don't make sense for everything, but in certain workflows, you can really stream data in and out of a GPU quickly and make certain changes to data more efficiently in that environment. So we're kind of excited about that. So I mentioned all of the software that is part of bioinformatics. this is a representation of what bioinformatics software we have on Pinnacle right now. And don't kind of ignore the size of the, typically that means which ones are most frequently accessed. I didn't have time to pull that up, so I just highlighted a few that have been used a lot recently, and I just, created I was feeling artistic one day, so I thought I'd throw that in. But you'll see a lot of tools in there that you recognize. Trim-O-Matic, Top Hat, there's GATK, and that's every time you pull up a new bit of data as a research project, as a gradient or as a faculty member, you start down this list of, well, I'm going to do this, I'm going to try this, there's a new assembler out, I may try it. How do I determine the quality of what I'm working on? And this is, if you follow the bioinformatics trends on Twitter or anywhere, you'll see these things just come daily. There's a new assembler, there's a new trimming tool, there's a new quality assessment tool, and it's just almost impossible to keep track of. So that's something that is not common to physicists and chemists. They're very set in their ways, and they have applications they've been using, for years, if not decades. This is very different for support from an HPC perspective. That's actually a snapshot of what we have software-wise installed on Pinnacle in the bioinformatics area. So all of the blue are essentially tools that bioinformatics people have requested be installed, and whether they've used them a couple of times or if they're used regularly, it's something that we got a support ticket on, and we're required to pull the software down, configure it, make it available, test it, and all in support of bioinformatics. So that's probably, without exception, the biggest difference supporting life sciences in high performance computing. So I mentioned the rattlesnake that I'm working on. Here's an example of just such a software stack, and I've left a few out, but these are the major stops on the list. So when you get Illumina data, you run something called FastQC just to make sure that what you had sequenced is usable. Sometimes it'll have adapters or primers left that you have to trim off. Sometimes there are just low quality areas within the reads. A lot of times, if your library chemistry gets a little bit old or weak, you'll have some poor quality reads on the ends of the strands. So you use FastQC to determine if those need to be cleaned up or not. Nanoplot is the same thing basically for the long read technology. You use Nanoplot to look at the quality of Nano or PacBio reads, and for the same reasons. Of course, typically you use Trim-O-Matic to clean up Illumina reads. Nanofilt is a good tool to clean up long reads. And just to quickly explain why you don't use the same tool, Illumina is very orderly. It's, if you order MySeq, then you're going to get a bunch of 250 base reads. Whether they're good quality or not is another story, but you'll know how many reads you have, and basically every read is a certain length. With long read technology, that doesn't typically happen. You prepare a library and you put it on a PacBio or a Minion or something, and you get all of these different read lengths, and they're all very long. Instead of 250 base pairs, you'd be 20,000 base pairs, 50, 100,000. People are generating 1 million base pair reads on some of these things now. So the technology of the software that you have to use to assess them is different because of the non-uniform nature between the two. Anytime you do something like a de novo assembly, it's different because you're pulling DNA and library preps and things from an unknown process. It's never quite the same process as you move from species to species, or from prep to prep, or from isolation to isolation. So the rule of thumb is always to try to use at least 3 different assembly programs in the beginning to see if one is doing a better overall job of building the complete genome than another one is. So it's kind of an assessment step, and it's just kind of been rule of thumb, over the years. So there are 3 more applications that you have to deal with, and those are just the 3 that I'm using right now. They found a neat way, instead of hand curating some of these things, they have something called a polisher. And polishers use consensus calling. So if you have an assembly, they'll use the pylon tool to stack up the Illumina data to verify, in fact, that the bases that you've assembled are correct. You know, it can actively change a base in an assembly based on the fact that the Illumina stack up shows that should be an A instead of a T or something, you know. So that's a consensus polishing step. Raycon does similarly the same thing except using the long read, so it's another consensus polisher. And then when you're through with your building and your polishing, you want to know if you have something that's representative of a draft genome, or if you should just, you know, delete all your files and go home. And Quast and Busco do that. Those are standard tools. Quast looks at things like number of contigs, how long the contigs are, the N50, the number of genes found, et cetera, to assess the quality of your genome. Busco is a little bit different in the fact that it's assessing single copy orthologs, so it wants to know how many of those genes that it finds are legitimately representative genes between a representative species, a similar species, and what you're assembling. So it uses a statistical process to determine the balance of orthologs between the two species. But that's just a long, that's probably overly deep in that, but I wanted to show that you definitely do need all these tools. There's not a tool that you can just go grab and say, I'll just use this one for this project. You're going to be faced with using you know, a plethora of software tools, and all of them have their own unique requirements, and none of them are the same when you the command line is different when you start to use them. So it's kind of it's a forever a learning experience. So wrangling all of that software, HPC has always classically been about, you know, with the chemistry and the physics. Fortran is still a primary language in those disciplines. You know, a lot of the heavy lifting in the code is done with Fortran, if not C. Some of it's been migrated to C for other reasons, but you take a single download of software, you pull down the source code, you build it with a compiler, whether it's a C or Fortran compiler, and then you've got a single binary. You know, that's your application, and that's what they use. As we saw in the previous slide, that's just not the case with bioinformatics. So we're forever looking at ways to make this a little more manageable, both from an administrative standpoint in HPC as well as a user standpoint. There's a lot of this we've determined that the users themselves can do in a fairly straightforward manner. So I like pretty slides, so I just threw some logos up there. But on the next, I'll explain what each of these are. So Docker is something that you find if you're using the, it's an OpenStack compatible tool. Docker is something that people will package their software in what we call a container. It's not exactly like a VM. It's much more. It's smaller and more efficient. It's easier to move around, things like that. You know, and it's easier to configure if you need to make any changes. But these containers can be run in a Docker instance on your workstation or a cloud resource, or there are a few research clouds about. We had one for a while at Fayetteville, and it was just kind of a test system. We don't know if we're going to do that again. But the Jetstream system at Indiana, part of the NSF cadre of research computers, Jetstream is a research cloud instance, and you can run these Docker instances on Jetstream. Due to the fact that Docker has security issues when running in a shared environment like an HPC system, somebody developed another tool called Singularity. Singularity is designed just to use these containers, but in HPC environments. So if you have a container you like that you've used on your workstation or on your laptop, Singularity can be used to migrate that container to where it works on an HPC system. So we can run containers on Pinnacle or Trestles, for example. Conda is a tool that was originally packaged with, for the Python people out there, I hope you're using Anaconda Python for your development and research. It comes standard with all of the most frequently used libraries that Python people like to use. And it turns out early on, some of these software developers in the bio world discovered that this Conda could also be used to install other packages outside of Anaconda Python. So they started using it as a package management tool. And this is now more or less what I use to install most of my bioinformatics tools. The people that developed the bio software have made them available through the Conda package management system. So rather than having to install 20 or 30 different libraries to support a piece of software, Conda just does a resolution on it. It says, okay, I know that you want to use the Fly assembler, and Fly requires these 7 other pieces of software to make it work. So we'll install all of them for you, and then you're on your way. So that's become very much a favorite of mine, and I'll show kind of an example here in a minute. Nextflow is something I'm just getting my feet wet in. Nextflow can use containers, it can use Conda, it can use compiled software, but Nextflow is a way of designing your own software workflows. So you could, in theory, all of those tools I showed you in the beginning, the quality assessment, the trimming, the assembly, you could actually put that in a workflow using Nextflow and let the system, the Nextflow would run on your compute system, and it would step through those steps by itself, making determinations as to what needs to happen next, and solving all of the runtime dependencies and things like that. So Nextflow is definitely on my short list of things to implement in HPC. That's I've been tinkering a little bit already. It's just not ready to put out for general use. So the Conda environment, and we won't dwell a whole lot on this, but I'll kind of show you how it works. Again, it's an open source package management system. Anaconda Python is free for anybody to download and install, which is the way I do it. Bioconda is an extension. Bioconda was created because the bioinformatics people wanted a place to start deploying their packages. So when they would build a new trimmer or a new mapper or something, they would package it up as a Conda tool, and they wanted a special place to put it. So Bioconda is basically that. It says below, over 7,000 bioinformatics packages ready to use, 850 contributors, et cetera, et cetera. So there's a lot of software out there, and it self-installs. When you tell it to install, it makes sure that it takes care of all the dependencies. Conda Forge is more of we do put it on there. It's more of a community-based contributions thing. So if somebody at ASU wanted to develop an application that they use a lot and they think other people would like, they could roll it up as a Conda package, and they would contribute it to Conda Forge, and it would come up in searches when people look for it. It would be hosted at Conda Forge, and people could download and install it from there using Conda. The installation, again, is easy. If you just don't use Python and you don't have a need for that large Anaconda Python installation, you can install this MiniConda, which basically gives you a few fringe pieces of things and the Conda installer. So you can make your determination. Again, do please stick with Python 3. Python 2 has been deprecated for a while, and that's still an ongoing problem with the user base, as people are trying to use something that's no longer supported. So definitely, if you have Python code, start trying to migrate it to Python 3. Even if you don't code in Python, go ahead and put the current standard on your system if you're going to use some of this stuff. So on Mac OS, you'd run this command. On Linux, it's this. So while Conda will function on Windows, there are very few scientific packages available in Bioconda or Conda Forge to run on Windows, and that's because Mac and Linux are basically the same thing. They're Unix-based variants, and that's where all of the open development tools and things are. So historically, these science packages are all developed on Linux for the most part, quite a few of them on Mac as well. And it's somewhat problematic to develop a Windows programming environment that will recompile those tools efficiently and effectively for the Windows environment, so people just don't do it. It's possible to do, but you would spend more time doing that than you would be just running it in a VM or something. If you are a Windows user, there is good news. So a lot of the bioinformatics community worldwide that are Windows users have been installing this Windows subsystem for Linux on their Windows machines. It's not a VM. It's not You don't have to choose one or the other. WSL, this comes up as an instance while you're running Windows, and it's a Linux environment that allows you to do these things, like install MiniConda and download applications. So there is people that use it really like it. I haven't had a Windows machine in over 20 years, so I haven't had an opportunity to try it. But I trust the community that's been testing it, and if you want to keep your Windows machine and do a lot of things on it, that's the way to go. So after you have Anaconda or MiniConda installed, you need to add the software channel so it knows where to look. Defaults is already installed, but they tell you to go ahead and reconfigure it. So you'd run these 3 lines at a command prompt, and then you have access to the software in all of these spaces. So at that point, you're basically ready to go. So a quick example, SAM Tools is a standard tool that almost anybody that's a bioinformatics person uses it for one thing or another. It's got a lot of utility functionality. So I just simply did a Conda search SAM Tools. It churns for a second and comes back and says, okay, how about the latest one, SAM Tools 01119. It's in channel, it even tells you it found it in Bioconda is where it's at. And well, that's what I want, so I tell it Conda install SAM Tools. It will evaluate dependencies and look at a few things in your environment, and it comes back and says, okay, here's what we would need to install to make this work. Are you okay with it? It'll tell you the other packages it may need to install, and it'll give you a space requirement. It needs, this will take 23 megabytes to install this and make it work. And you tell it yes. And then once it's completed, you can do your typical which SAM Tools, which is a Unix command to figure out if you have a package installed. And it says, yeah, it's in Users, JPummel, Anaconda 3 bin, SAM Tools. You're ready to go. It's right there. Do whatever you're going to do. HPC is a little more difficult. We have ours set up where this works fine, but HPC, a user can install system level software. And by default, if you just did this command above, this Conda install SAM Tools, it would try to write some things to space on the supercomputer that you don't have access. So what we do, we create an environment. So there's a similar general Python directive to do environments, but Conda has its own. So if I say Conda create -n, I don't know why they picked n, but it's going to create an environment. I call it Unicycler for the Unicycler assembly pipeline, and then I want to download the tool Unicycler. So it'll do that. It'll create this environment, and it'll download everything I need to use Unicycler. Then on the HPC system, you say Conda activate the Unicycler environment. I want to use something that's in that environment. So it's out of the way and just resting until you tell it to be activated. You activate it, then you have access to all of the tools in that distribution. So you run your assembly, and then you just deactivate it, and it's out of the way until you need it again. This is all you ever have to do at that point is activate and deactivate. Once in a great while, you'll run into a package that has some oddities that they haven't, something is broken or something, and you need to know specific versions. So for this one, the Busco software that does the single copy ortholog assessment, I wanted to install it on Pinnacle. So we did create -n Busco. Told it I had to do this for some reason, and I don't remember why, but I specified the channels. I needed this version of Busco. It would only work with an older Python. I had to step back one version on BioPython, and then the Augustus Gene Finder needed this version to work with this stuff. So it was problematic, but once I told it what I wanted, it went out and looked at the whole array of software and the software that's needed to support these and said, okay, yeah, we can do that, no problem. So I hit yes, and I just finished up a 4-day Busco run on the snake genome, so it's still certainly the most efficient way to install software, and I'm increasingly a big fan of Conda. So we're getting close to the end of my spiel. Some of the things that you can benefit from as far as AHPCC resources, we typically set up an account within 24 hours. It's often 2 or 3 hours, just depending on what David and Pavel are doing. They do all of I haven't done any system administration stuff in 10 years because I'm neck deep in the science and the the communities doing things like these presentations, working on projects and stuff. But David and Pablo will typically have you set up for sure within 24 hours. There's no cost here. Everybody's at an Arkansas institution or affiliated with somebody at an Arkansas institution. If you have a help request, you send it to the HPC support, and it's very common. I always hesitate because I don't know if the guys want me saying that, but you'll typically get a request or a response to a request 7 days a week. It may be some odd time, but even on Saturday and Sunday, if something's crashed or if you need a quick pointer on doing something, we're all watching the website or the help support site. So we're pretty active in keeping people moving. We always are looking for low friction solutions to make it easier for people to access HPC and be effective and get their work done. Web portals. The Conda environment is a simplified method of allowing people to put their own software on the system. The administrators, David and Pablo, will certainly install something in system space using Conda if you request it. But if you don't want to wait, or if you're just like having your own little bundle of software, it's totally fine to install it in your own user space. We try to spend some face time initially for new users, and typically that's the easiest way to go. So even if you've logged into your account and kind of found your way around, just a 15 to 30 minute, well, in the case of COVID, it will be a Teams meeting or a Zoom meeting, but spending 15 to 30 minutes sharing a screen, you're pretty much up and running. You'll run into some odd things along as you progress, but you're doing meaningful work and turning out data, and doing research. We used to hold domain-specific workshops, so I did some of these for genomics people, where we would take a half a day when we would go through Linux 101, and then we'd do some of the introductions to HPC to show how HPC works, and then we would do a short introduction to a genome or transcriptome assembly with a reduced data set. So you'd gone through a representative workflow from start to finish, from logging onto a machine to analyzing a small assembly or something. So those are still possible. We just need to retrofit them to be virtual instead of face-to-face, due to the fact that we're probably going to be middle of next year before we're back on campus. We provide you basic job scripts. So to run something on a computer, you have a simple text-based script that sets up the environments. It chooses the computers specifically that you want to use. It loads the software stacks that you need for that particular task, etc. So we try to provide you a basic job script that you can modify to your own use and take that down a bit. We do like to show people how and where to look for solutions to common software errors or HPC errors. Looking at your own errors certainly gives you a lot of insight to how to better use HPC. We certainly don't just leave you with it. If it's not pretty quick to resolve, we don't want you being frustrated or floundering around looking for solutions either. It is on our side of things. It's something you're trying to get HPC to do. So if the answer doesn't come to you pretty quickly, we'll jump in and do a search and maybe log on as you and run the simulation too, so we can see the steps that you took or something. But yeah, we do encourage users to learn about the intricacies of running scientific computing jobs. And then I've had for a long time, I guess 2014, I started an HPC Bio mailing list at Fayetteville. And it's not Fayetteville exclusive. Anybody that wants to be added to that mailing list, I'm happy to do so. I post, even during COVID, I usually post 2 or 3 postings a week, and it might be a new research paper on genomics that came out. It might be something about a brand new tool that people might like to try. It may be an announcement from a sequencing center that they're running a special on sequencing. It's any number of things. It's not very, you're not limited from posting on it, but people at Fayetteville have just chosen not to do that. They say they like the flow of information coming to them, and they just like to leave it at that. So nobody ever really posts on it. But when I tried to shut it down at one point a couple of years ago, they said, no, don't do that. We like getting that information. So if anybody wants to be added to HPC Bio, you can certainly just send me an email, and I'll put you on the list. It's pretty minimal. Again, 3 or 4 emails a week max, various subjects. So if you're interested, happy to do it. If you want to be an AHPCC user, academic institutions in Arkansas and affiliate researchers, if somebody in Arkansas will sponsor them. So the first link is for internal right now is people at UAF, external is anybody else. That's changing slowly because some of the chancellors have been having a discussion about unifying common resources, and there may be some networking on the computer side that will start making that more transparent, shared AD logins or something like that. But for now, if you're a UAF person, you use internal, which uses our campus login authentication to let you in. Externally, Pavel will generate temp passwords and things until we get some of these other tools worked out. We're looking at maybe using something like the Uncommon authentication stack to allow this to be a little more straightforward. But yeah, if you want an account on HPC, you just click this second link and fill out the web form. Then whoever your sponsor is would approve it, and then Pavel would generate the account. On HPC systems, you get 100 gigs of replicated, or it's not really backed up, but there's a duplicate of it somewhere that can be restored pretty easily. So that's your home space. We don't recommend that you do computing out of your home space because, again, that file system is not really designed to do that. We're pretty generous too with storage space, so you get 10 terabytes of that. And that's up to the discretion of the administrators. If you can justify why you need more for something, that they can do that. Please look at the STAR, especially since this is becoming a big deal. Storage of controlled data, HIPAA, ITAR, any of the COI stuff is prohibited because that's a huge fine if a researcher or a center is caught handling that type of data without the proper protocols in place. Historically, AHPCC has been an open science, open research platform, and for the most part, it will stay that way. We may find a way through encrypted virtual machines or something to do more secured data, but right now, and I think all of the big clusters in Arkansas are not really certified to run what we call controlled data. That's a huge fine from government agencies if you're caught doing that. So again, I think you have to say yes when you ask for an account. But yeah, you should not be using controlled data on HPC for now. And we're also happy to assist in connecting users with the big national supercomputing centers. They also are NSF funded, and there's no charge for running things on those systems. Those systems are an order of magnitude bigger than what we have in state. So when you need a very large simulation, or if you need a unique hardware resource that we don't have in state or something, I use it actually because if there's a waiting line on Pinnacle, I just move the data over to one of the national centers, run my simulation, and pull it back. So I get impatient on my own system and just use somebody else's. But those are, again, free, and they're very well supported, very well funded, and top of the line equipment. So we're happy to help you write a grant proposal. It's a startup application is 2 pages, I think, so it's very minimal. And I'm certainly happy to help you with an NSF exceed allocation request if anybody needs it. And essentially, other than that, there's the contact information for AHPCC, general queries. If you have an account, you can send requests to HPC support. The website, we don't have a permanent web developer, so it's kind of hit and miss. It looks pretty good right now, but we need to get a warm body in there to keep it cutting edge. And then I do my best. There are a lot of really good bioinformatics people on Twitter. They talk about research projects, they talk about software. I try to keep up with HPCC's Twitter link. I will do a good job, and then I'll miss a few days. So it's kind of a best effort, but you're certainly welcome to follow us if you feel so inclined. And with that, Liz, I'll turn it back over to you.
Jeff, thanks very much. Let me just open it up. What questions do we have from the audience? Anything that you have, Jeff, here that you'd like to ask him?
Jeff, I got a question for you.
Sure.
On one of your slides, you had the home versus the storage space, and they were obviously much different, 100 gigs and 10 terabytes.
Yep.
When I'm actually on Pinnacle, where does the storage exist, and when I'm in which file system?
Yep. The way that they configured the disk arrays is a little unusual, and it's counterintuitive. Let's see here. Whoop, that's not what I wanted. Hold on. I'll send you a link to that, but it's also the destination to that. You can create a shortcut, and I'll send you an email on how to do that. But storage is actually /scrfs/storage/your username. So it's totally counterintuitive.
Okay.
And actually, your home directory is under that. So I'm not a huge fan of the way they've done that, but there was some technical reason that it had to work that way. So yeah. And then to follow, something I didn't mention in the slides is if you're running a very big simulation, you don't want to run the simulation out of storage either. That's kind of slow disk. If you have a big simulation, then you let the scheduler move it to what we call scratch space, or you run on local scratch on a node. So yeah, that's why it's always easiest to have a 30-minute, once somebody gets an account, we kind of get a shared screen and we can show all this, because there are all these little irksome details that are hard to put in just a presentation or something. But yeah, you're close. Just go to SCRFS storage, your username, and then you can put all of your data there for staging.
That's not backed up?
No.
Okay.
The problem with backup, most HPC centers, even the large NSF centers, don't really back things up, because we're talking about, with big research projects, it's terabytes or tens or hundreds of terabytes, and it costs as much or more to back it up as it does to store one copy of it, because you have to have a duplication of the disks or tape, and you typically have an expensive software solution that manages the backups. And when it comes down to it, people are more interested in timely computation of their data than they are storing it. So they say, well, if you have to spend the money, spend it on more computers instead of backup disks. So it's kind of a decision made by the research community.
Okay. And then just to clarify, everything within your home folder does have a backup.
There's a replication of it somewhere. I don't know how they do it, but they say that one is safeguarded in some form or fashion.
Got it. Thank you.
Other questions on people's research needs, expectations, things we can do to make your research life better?
Well, I'll ask another.
Sure.
Regarding what you just said about writing to scratch, where is that file? Is that?
So scratch is, to do the scratch thing, you have to actually write that into your job submission script.
Okay.
That's another, I won't go into detail about why, but basically people like to write things to the expensive scratch drives. They're all SSDs or NVMEs that are expensive. People like to write things over there and then not clean up after themselves. So David and Pablo finally made the move that only a scheduled job can, the scheduler itself, Slurm in this case, actually when it starts, it says, he's got some data to move. I'll move it over there for him. And then they've got a script that comes up later and cleans up after you. So it's very automated, but they won't let users directly write to the expensive scratch drives themselves.
Yeah, I was trying to write to it, and it said I was denied.
Yep.
And you just said we should write to it, so I was confused.
You do, but you do it through your job submission script.
Okay, I might need to get some of that information from you.
Yeah. If you're starting to work on some projects, I need to give you a base job submission script and show you how to move the data back and forth with the scheduler.
That'd be great.
Okay. Kyle's finding all of the seedy, dirty little secrets of HPC that plague all users all over the United States and the world. Any other questions, comments, anything I can do for anybody at this time? Something we could mention that I don't know if it would be, I know Kyle's interested. We do also have a program called the Condo program at UA Fayetteville. I don't know if UALR or UAMS do this or not. We allow people that need a lot of compute time and need unlimited runtime and high accessibility to compute resources. We allow faculty members or labs to purchase equipment that we install into HPC and manage for them. The caveat is that when they're not on those resources, the rest of the community can use the resource for a short period of time. So if one of the biology labs has bought a couple of big nodes for genome assembly and that faculty member is not using them, Kyle can log in and run a job for up to 6 hours is kind of what we've set. You can run a job for up to 6 hours on somebody's condo resources, and then their priorities kick in. You know, you might, even if you had 100 jobs waiting for that resource, if the owner of the resource submits a job, theirs goes to the top of the list and they can run for as long as they want because they own the equipment. And that's kind of what you and I have been talking about for a piece of equipment for a class. And the 6 hour thing is what we need to talk about, as far as you don't want that happening while you're trying to run a class. So that's one of those things we're kind of tweaking a little bit. We still have to work out some details at Fayetteville as to extending the condo program to non-UAF people. But again, under the guise of this one Arkansas research initiative, I think there's some discussions ongoing about being able to offer any service that any campus has to other campuses.